That's what it's just a weird schedule. Trying to figure it out. So here they
Wow, dazzling.
Like just
No wonder you have the lights down in here. You don't need them with this projector. Okay, so let's get going. What I want to do is we were in the middle of the briefing just describing the course. Don't want to cheat that because it's really important. And then I have, fortunately, the next deck is very short. So hopefully get through all of that and call it a day. Still won't get to any real AI that you could actually code up today, but by the end of the week, we'll be heading down. And then on Friday, there will be a lab. It will relate to Hamming, so do all sign up. If anyone happened to miss it, it's one of the earlier slides. There's a link in there. Go over and sign yourselves up. They tend to be very, very good about getting people sign up quickly. Any issues that I may not be aware of? All right, then let's roll on. This is the course on the slide here. Now, depending on your background, you have a lot of CS, you have an interest in AI, you may be able to understand pretty much what we're going to do in the whole course. Other people, it's not so important. It's an attempt. It's an attempt to tell you what we're going to do up front before we go do it. If you don't get all the details, that's fine. But let me talk through it. So we're going to start. This is an intro AI course oriented towards simulationists. So we're going to start with systematic search. So this includes the simplest form of AI, which I think any new simulation platform at a very minimum is going to use AI to do pathfinding. No one wants it. In the old days, when we had a simulation, we wanted to move from here to there, you had to go and click, and every time there's a corner of the road, you had to go and lay a breadcrumb, and then your units would move like that in straight lines in between the breadcrumbs. Okay, we're well past that. And these days, people expect that to be automated. Maybe you want to adjust the path after the AI produces it for you, but you expect that to be produced for you. This kind of search is systematic. It always succeeds. If there's an answer, it finds the answer. And we know quite a lot about it. In this unit, we will reach the apex for MOVE students that have not had other CS training. We will reach the apex also in algorithmic analysis. So CS has a long tradition and a lot of experience with how do you actually apply math in a meaningful way to understand algorithms. And a lot of questions really kind of, just to be clear, like in every area of science and tech where you apply math, I mean, we have all these questions as practitioners. We would like to have an authoritative mathematical answer to. You're not going to get answers to all your questions. The mathematicians come in and say, oh, we can answer this, and then we can answer something over here. But those are like pole stars for us, because that is like mathematical knowledge. It's incontrovertible. It doesn't change over time, and it allows us to better deal with all the other issues, which we're not going to get mathematical help with, really. But we'll be able to navigate it better for our exposure to the math. So we will be doing some of that. This is stuff having to do with algorithmic efficiency. All right, why do you pick one algorithm versus another? Often efficiency. Now, you just came through, if this is your first exposure to programming in a serious way. And honestly, for all of us, on an average day, we're happy if our programs run. If it like runs and does something that looks right, it's a good day, okay? But for more serious applications, when there's multiple ways to do things, how do you pick amongst them, right? So there's a school of thought behind that, and you'll at least get exposed to it a little bit in there. And also, if algorithms actually have proofs behind them that they are optimal algorithms, that is very rare. But the main algorithm, which is A-star search, for those of you who have been exposed to that already, the main algorithm does have a proof, and we will go through it, and you'll be amazed how simple it is. It's quite powerful, and in that case, tells you one of the things that we as practitioners really would like to know. So now, we'll start with that. And then we will go to game solving. So what's the connection here, right? So search for pathfinding, right, from point A to point B. Well, if you think about it, that is not yeah, if you're willing to be generous to me, that's not all that different from the kind of thinking you do to make a plan, right? We start with the state of the world and we know where we want to get to. We start planning actions that are going to take us incrementally to that desired future world, right? Okay, and that is the connection. Now, the mathematical and algorithmic tech is not identical to what we use for pathfinding, but it is a close relative, so that's why we'll handle that next. And we will do some advanced stuff with game solving that involves actually pretty cutting edge neural networks and stuff like that. But we'll leave that for later after we actually cover the neural network technology. After systematic search, we will talk about hill climbing search. Okay, so what's the difference? It's search and it's search. These algorithms are incremental. They come with no guarantees of finding the best solution. What they do guarantee, if there is a guarantee, is that every time they change your solution, they will take your draft solution and change it. It will be for the better. Okay? But these algorithms are generally locally optimizing. The best you're going to do is when the algorithm stops, you know that any really close relative of that plan, of that path, or whatever it is you're generating is worse than the one it gave to you. But that doesn't mean that there's someone very far off in problem space that is much, much better, unfortunately. That's the reality of these algorithms. Now, that may sound a bit scary, right? So I get an answer, but there might be a really, really, really arbitrarily better answer somewhere else. Gosh, what use is that tech? Okay, this is the tech that's behind all the AI that we're using these days. When we train a neural network, this is the kind of tech that we use. We don't know that there isn't a much better solution over the horizon that we just didn't see. There's no way. And we've been looking for that would be like the holy grail for neural network trainers. I've been doing neural networks since the field began in the when was it? The 80s, modern neural networks. Okay. All right. So after we talk about this general search technique, we'll head into its main application, which is training a neural network. And this is the main application here, neural network regression. Regression as in what you may have covered in your statistics coverage. Okay, like linear regression. You've at least probably heard of linear regression. Well, what's that? Got a bunch of points, fit a line. Okay, so this is got a bunch of points, fit something that's not a line, but actually is a more complex curve, and maybe often in a high dimensional space. Okay, are you excited to do regression? Does it sound exciting? If you're really excited by that, you probably are in the wrong classroom and need to go over in the OR department. So mostly on our side, we want something that's a little more teeth to it than just I fit a curve to some data. Okay, why do we use that as the basic example? Okay, because all applications of neural nets, almost without exception, this is what the neural network is doing. Nothing other than this. It's fitting a curve to some data. And then we apply it to do things that look very, very different. Okay? But under the hood, and this is what you should be getting from a basic class, you should have the insight to realize that, oh yeah, all these things, generating images or talking, understanding human speech, the list goes on and on and on. Under the hood, if it's a neural network, it's always just doing regression. Okay, so if you can understand this is a magic touchstone that's going to help you a lot understanding what's going on in tech these days. And of course, and by the way, the advanced examples in this course and in the summer course. Okay, now the very next bullet here, reinforcement learning, is something sounds a little more interesting, learning to take action. So that's what we need. We have a simulation. We want the AI to stand in as a sparring partner. We want the AI to help us figure out, help us do signal processing, to help us understand images. All those things can be considered actions, and many of them can be put in this kind of a framework called reinforcement learning. It's a very broad umbrella. Under the hood, the neural networks are always doing this, okay? But now finally we get a network that's either going to take an action or maybe just recommend an action to a human user. You should do this in this situation, okay? And this is the reinforcement learning is one of the key, the buzzwords that's always tossed around these days. when you look and hear that AI is doing something cool, often this is the very next thing. The very next sentence will say something about reinforcement learning or a neural network. Okay. Then we'll be ready to do advanced game solving. And then at the end, it's just kind of welded on. Again, this will be brief, but I just want to do a little something with generative AI, right? Because this is the AI that's very impactful right now. I know how careers tend to go of our students. I've been here a quarter of a century, and you will go somewhere where you will have some other job, but they figure you're the smart person who got to have the education, so help us figure out this technical problem, which is not a simulation problem, but it may very well have to do with generative AI, because that's one of the things all the commands are trying to figure out. How can we get juice out of this? How can we get more juice out of this? So we'll talk a little bit about text and the underlying technology used to generate text. I'm talking about your Chat GPTs, your Geminis, what have you, okay? And then just a little bit, this is just new, maybe just a slide or two on how image generation is done through a technology called diffusion, which is only one of the technologies that's out there, but it's the dominant technology right now. Give a few years, probably something else. Okay, any questions about this? This is your whole quarter, pretty much. All right. All right, now what are we going to actually do in the class? And let me try to give you a little guidance about this. So the lectures are the bulk of it. Okay, we used to go and try to read the textbook, but it's too slow and a little too detailed for most of you, unless you're the rare student. We do have some come through here eventually do a PhD and stuff related to AI. In that case, it's good pain to go and try to read the Norvig and Russell book, but for the rest of you, it's a bit much, and it really slows things down. It's a weighty tome. Great reference. Again, it's like, as I said, I won't go back on what I said. It's like if you're going to have one book on your shelf on AI, that's not a bad book. Russell, by the way, is one of the most senior AI professors that's still in the business. He's at Berkeley. Norvig is was the head of AI for Google for years and years. And even before that, I knew him from his very excellent writings on how to properly code AI. So, and it is the dominant book that's used in your MITs, your Stanfords, your Berkeley. I mean, that's it. That's the main book. Okay. Now, we're not going to do that. That's optional. You can do that yourself, but the lectures are not optional. That's the main meat that I'm going to try to convey to you. There will also be some homework to guide you through this, but this is where I want to communicate how I see an intro. This is a 3,000 level course. This is still an introductory course. How is this different from an undergraduate introductory course? So this is different in that in an undergraduate introductory course, if you go through and you will sit in all the lectures and you do all the homeworks and you can do it all, you can expect an A on the final. I mean, that's the whole intent. You did all the homework, you know everything you need to know. Okay, there would be way, way, way too much homework if I had to design this course this way. Graduate courses are typically not done that way. We rely more on the lectures and on your realizing that, well, I don't really understand that lecture I just heard. Okay, contact the professor. You're always welcome to contact me, and students do that way too seldom. Beyond that, you got your Chat GPTs, you're just Googling for information online. There are excellent, you go onto YouTube for AI videos and look for the high-rated ones. Some of those are really excellent. There's a lot of other ways you can go and enhance your knowledge. Okay. Now that may just seem lazy to you, but again, it's not, because there just isn't time, because I'm relying on the fact that you will be able to go through and say, I understand that was perfectly clear for me just from seeing the class, that one. This other thing was complicated, but I went through it in undergraduate. I know it well enough. I can skip that one, and you can focus in on the stuff you need to focus on. Okay. Now, if nothing in this class is easy for you, I doubt it will be for too many people, but it might be, depending on your background. Then great, focus on some other course that's harder, or go and do professional education. We're relying on you to be to control your own time and make the best use of it. I think that's the only way graduate education works. We can coach a little bit, but really graduate education is very student focused. You are your own instructor in a very real way. Okay? All right. There will be labs. To me, in some ways, the labs are always the pinnacle in a tech-oriented course because you actually have to do something in the lab that proves that you understand some aspect of the tech. Okay, there are normally 4 in this class, but the first one's, I don't forget if I called it, often I'll call the first one Lab 0. It's not like a really full-fledged lab. There's no real AI content. By Friday, you're not going to know. I won't have taught you anything to say, now prove to me you know it, right? It's more, you know, crawl from crawl, walk, run. You know, it's just making sure you can get on Hamming and you can do some of the basic analytical types of things that you'll need to do later in the course. Okay, and also lets us, and I'll ask you to write a lab report, which will let us communicate, you know, in a relatively low stakes way about what should a lab report have in it, right? Are you producing the kind of thing that I expect before we go on to the real AI and the real more higher stakes examples? Okay, there are some tests as well. As I said, there is some homework, but it's very scattered. Where I do put homework in the course is, again, you understand what my philosophy is. Where I put it in is where the overwhelming number of students have not been able to master that point without some external assistance. That's where I will go and assign some homework. Okay, so the way this works, because the first subject, the systematic search, that area is a little more cut and dry. The homework does a little better job preparing you for that first test, but don't get complacent because the second test, when you get into the neural nets and the stuff like that, it's a lot harder to go and make homework for that kind of a thing. A lot of the learning is done in the labs, but I still am going to give you a test. So we will have to rely on you reading the lectures and asking questions or what have you if you need to go deeper or get some augmentation on the what I say in class. Any questions about that? I know everyone does it a little different, and sometimes that's awkward. But yeah, communicate if it's not working. Yeah, we'll make it work. Okay, so this is a class on AI, so it would be very awkward to tell you not to use any AI tools. So I will tell you the opposite. As I like these tools myself and use them almost all the time and ask them all kinds of unreasonably difficult questions. I don't take what it says back to me as gospel truth because it's generally not, and they can be wrong in just ridiculous ways. And often, and this has been a pattern over AI, as I'm skipping the AI history, but one of the patterns in AI is the stuff that we find difficult as people is often like the easiest for the AI. Like one of the earliest things way back in AI history in the 50s, one of the first impressive AI programs did proofs in logic. And you all had some logic, right? It did proofs in logic. Doing proofs in logic is not trivial. You know, I'm not talking about, you know, A implies B and A, prove B. You know, I'm not talking about that. I'm talking about a really complex proof. Okay, that was mind-blowing. And when people saw that, and this again is the reason for all the AI disappointment, they're like, well, that's the hardest stuff I've ever seen. It can do that. Well, it can do anything then. AI can do everything. That tends to be the pattern. And then people realize, no. The stuff we find easy, often the stuff the AI still will struggle. Okay. And that's also the pattern that I've seen in my own research. But I still find it, I wouldn't be wasting my time typing in a long prompt to an AI and then reading through the page full of stuff it dumps back at me if I wasn't getting some value out of it. And I do generally feel that I am getting value out of it much more than I was getting out of just a Google search, because you can be so much more specific in a paragraph than you can with just a few keywords that type into Google search. Okay. So I feel like win or lose. Either it's going to help you and you'll get smarter about AI in the course, or you'll see it fail, which is also helpful information, maybe more help at this point while we're all, including me, forming an intuitive knowledge of where the AI should be trusted more and where we really want to trust it less. When it comes to test time, though, we will still do pencil and paper, right? Because the model still is, you know, I'm supposed to be improving your individual capabilities, right? This will change over time. In the same way, no one would argue with if I let you use a calculator in the test that I'm not testing you. They wouldn't worry that it's actually the calculator that's smart and it's not you. Okay, in the same way, I feel pretty confident in the future the AI will just be considered. You'll be a system. You and your AI buddies will be a system that will get tested together. But we have to be a lot smarter about the AI, frankly, to do that. We're just not there. And so I would be remiss if all the things so for some stuff I do, like the labs or whatever, you'll be able to use the AI. But for other things, it will be it's incumbent on me to do better than that. Okay. Now, I will say when we get to the lab, I mean, what I consider out of bounds is you can use the AI all you want, but you should use it more like you use a classmate, right? You're allowed to talk amongst one another about the subject you're learning, right? That's expected. And normally, at least in moves classes, at least all the ones I know, it's okay to even ask for help for a specific thing that you're trying to do. What we discourage is, don't ask, what should I do for line 1 of my program? Oh, thanks. What should I do for line 2 of my, right? And like somehow completely circumvent the intent of you getting educated, and it's just the buddy who's doing all the work. Of course, in the extreme case. That would be very dangerous to do that with things I'm assigning here, but in some cases you probably could get away with it. But don't, because you're cheating yourself. All right. Okay, I think I'm going to stop there with that deck. I need to move to the next one. Okay, so next topic. There is a word called the agent word. Is that, how common is that? If I talk about, we're in an AI course, if I say the agent, does that sound like you know what I'm talking about, or you feel like what is the spy class now all of a sudden, or is it common? You feel like you all know?
It's common to hear it.
It's common to hear it?
If I could give you a definition of an agent.
Okay.
From the definition I give you of what generative AI is.
Fair enough. Well, you'll be able to define it, at least to my satisfaction, in 15 minutes. Okay. But yeah, so agent is it basically means AI. It means it's a program. It's an AI program. That's what it is. But it comes from a certain perspective. And that's what I'm going to try to convey to you with a few slides here. I'm going to give you a few sketches, which I hope will be useful to you throughout this quarter and into the summer quarter, the advanced course, and together with anything else you might do related to AI if you get involved with building an AI system. So they're basically architectural sketches, different ways you can think about building up a bigger AI. Still too vague to actually go and build right from those sketches, though, way too vague, but I think it will help. And then I will end up with some terminology for environments, which I found useful, and I will use this quarter just in terms of what tends to make problems hard for AI versus less hard. Okay? All right. So, all right. So what is an agent? Okay, here we are. And so it's an autonomous program, but I'm going to define exactly what I mean by that in a minute. It doesn't necessarily mean it's like a main V or something that interacts with an environment, be it the real world or software. So this is meant to include physical embodiments of AI, like a robot, okay, but also just software. Okay. Now, this terminology is mostly borrowed from robotics, which was mature before the modern era of AI. So we just kind of stole all their terminology. So agents are often said to have sensors. Like for a robot, that means a physical device used to perceive the world, like a camera, infrared sensor, a microphone. Okay. In software, the analogous thing would be, let's say it's just a software program where you type in math questions, word questions, and it tries to answer them. Okay, well then your keyboard is providing the input, right? Or maybe you write it into a file and the program reads the file. That's fine. Or maybe you're talking over the web or over the internet more generally, and you're using sockets and pipes or that sort of thing. Okay, those are sensors. Okay, you affect the world via effectors. So for a robot, these are typically also called actuators, and it means things like the motors running the grippers and the wheels of the robot. And for software, the way you affect the world is often by affecting the user, which means we include the screen, the files that get written, again, communications over the web, over the internet. Okay. Now what the sense in which agents are autonomous is that all computation in between what comes in here and what goes out here is strictly inside the program, right? So in that sense, it's autonomous. And if this can mean a real mobile robot that really looks and seems autonomous, but hopefully you buy that, okay, yeah, even a program that's doing some lesser type of AI, less impressive type of AI might still be considered to be autonomous in this sense. Now, what we need, this is supposed to be agents are engineering concept. So part of this is also that we assume that there is some kind of a performance measure, a number that's available that we can use to say this AI comes up to this level, this one's a little better, this one's a little worse. Okay. All right. So percepts. So that may be a new word for some of you. Perception, you know, right? So a percept is supposed to be an atom or a quantum of perception. Okay, that's the data elements that are coming in from the sensors. Those are the percepts. Okay, and therefore it should make sense that the total set of data gathered up to the current time from when the system was turned on is known as the percept sequence. And this lets you do a kind of a logical decomposition in your head. So if the AI was not pre-programmed to have this little bit of knowledge, and if it didn't come in via the percept sequence, then it doesn't have it, right? So that's all the AI has to work with, what it had when it got turned on and its percept sequence. So conceptually nice and clean, and sometimes practical. You think that way. Okay, performance measures. So there are various kinds of numeric performance measures you can put on an agent. Okay. Usually, often, we hope that the agent is going to maximize that measure. Okay, it's a measure of goodness. Okay, if we expect that, then it's a good idea, where we have the luxury at least, to let the performance measure be a function of the percept sequence only. So if the agent is being graded on information that it receives, then it should know where it is at any point in time. And that's good for an agent to have them, to have better success. And I think we can understand that this is the kind of situation that we would like to be into. I mean, it's kind of ideal, right? If you're being, if you're get a yearly performance review and you know exactly what you're going to be graded on, and it's visible to you at all times, your progress, no surprises. You didn't make it? Well, you've known you're not making it. Okay? Now, this is not always practical, right? Think about this course, right? I mean, there'll be tests. There are things that will not necessarily be instantaneously available to you in terms of your incremental progress. Before we do our first assessment, it'll be a while before you get any feedback. You may be thinking, oh, everything's all fine. And then you get the first grade. And it's like, oh, wait, professor doesn't think it's fine. What's going on? Right? Okay, this can happen. It's not optimal, but that's often a practical necessity. Okay, when we talk about an agent being rational, so this is a goal of agents typically to be rational. What we mean is that they act to maximize their expected performance, that number. Expected in the sense of statistics, right? It's a random variable, okay, that isn't always under the agent's total control. So it should act in a way which makes sense, and in average circumstances at least should have provided a good result, even if it didn't in the actual way the world went. It was unlucky. Okay. All right, so let's do a kind of a whiteboard example. just to be sure we're communicating on all these elements of an agent. So this is meant to be an agent. This would be like some kind of abstracted vacuuming robot. We're kind of looking down, and what we're seeing is a vacuuming robot, and we're seeing low walls, and we're seeing some arbitrary division in the squares. That's going to make it a lot easier for us to, to talk about this. I'm seeing some messy places that the vacuuming robot hopefully will solve. Okay. One special location here is called the home for the back for our backbone. Okay, so we can now go down and try to answer all these questions, or I should answer. I'm the one who's conveying the information here. So, like, what? But you could be asking, right? Now you have the definition of an agent. You say, well, okay, it's an agent. So, what are the sensors? What are the sensors? Okay, so let's say we've got 3 sensors. We've got, if we bump the wall, if we try to move forward and bump the wall, we get this sensor tells us. If there's dirt underneath the back bot, which doesn't look like there is right there, but there would be if it was over here, then it knows from the sensor. Okay, and it also knows if it's home or it's not home. Okay, now effectors. Now, if this were really a robot, the effectors would be the motor that drives the wheels, and then maybe the angle of a wheel in the front of the back bot to turn it. Okay, but this is abstracted, and that's okay. So it's fair to go and abstract the sensors and effectors to suit your purpose, okay? And which is what I'm doing here. I'm going to assume this thing can just move forward, or it can go right, by which I mean a 90-degree turn right or a 90-degree turn left. It can suck, turn its engine on, or it can shut itself down completely. Okay? All right, sensors and effectors. Okay, it's in an environment. Okay, in this environment, we have the underlying grid, might be considered an element of the environment. We have the walls, we have the dirt, we have the home location. And then the performance measure, I would define it, it's often defined in an incremental way, which is what I've done here. So we'd say we start with a 0 score, and then every time you suck up some dirt, okay, we'll give you plus 100 to your performance score. Every action is -1. Why might that be?
You want to do it in as fast as possible.
Right, right. We're consuming electricity, right? So that isn't free. So we don't want the agent just to be spinning around endlessly. And my pet peeve is when these things shut off and they're not in their home location. So you stumble over them and makes you have a bad day. So if it does that, -1,000. Okay. All right. Any questions about this? It's clear enough?
Does it know where the dirt is?
If it's on top of it, it does, but if it's not on top of it, it does not.
Just a room. Right, just like a room. Is that what
Kind of, yeah, very similar to actual vacuum cleaning robots.
So all around the
ye-
house. Don't clean nothing.
Okay, so let's just, what I've got next is just a little exercise for us to do here. Okay, what does a single percept look like? In other words, in terms of data, like how much data is in one percept? So, do we get the percept concept?
Well, if it does an action, it should receive a percept.
Yes,
And
and
the
what would be in that percept?
Should have a sensor input from every sensor.
Okay, and how much data would that be?
The
Okay, and what would, in your favorite programming language, what type of data would that be? A bool, right? And, you know, if you're thinking very low level, those would actually be 3 bits of data. Bit could just be 1 or 0, right? Okay, so it's just 3 bits, very little data in each percept for this particular example. Yeah, okay, I agree with that. Okay, and then it says, let's assume the bot takes these actions. Let me just put it in code here so we can go and do it. Forward and suck, and forward and suck, and what else? Forward and suck again. And then off. Okay, what's the percept sequence and what's its performance score? Okay, so let's assume what I normally assume. Whoops, wrong direction. Let's assume that as soon as you turn it on, it gets 1 percept, right? So before it moves forward, it gets a percept. What would that percept be then?
0, 0, 1.
0, 0, 1. Okay, good. Let's use zeros and ones. That's fine. Okay, so it'll be 0, 0, 1. Okay, and now it moves forward. Okay, and it gets another percept. And what would that be?
0, 0.
One,
Well, 0, 0, let's see. Did it just bump anything? If it tries to move forward? No, it can move forward. There's no wall. So 0. Is there dirt here?
No.
Okay, so 0. Is it home? No, so 0, 0, 0. Right? All right. 0, 0, 0. Okay, now we turn on the engine and try to suck up dirt. Okay, there isn't any dirt, but oh well, that's what it does, right? So what would be the next percept? Same thing. Okay, and if we move forward again, what do we get? 0, 1, 0, because there's dirt, right? Now we suck, okay, and what do we get?
0,
0.
0.
Well, if it actually sucks up the dirt, let's be generous and say it sucks up the dirt, then 0, 0, 0, right? Okay, and one more forward suck pair here. Okay, so forward it's going to be 0, 0, 0, I think, right? Sucking is still going to be 0, 0, 0, and then it's going to turn off, in which case it doesn't get a percept when it gets it's off. Okay, all right, and now we can turn this into a score, hopefully by going down and figuring out what it does, what it's done, and scoring each action. So it's -1 per action, so it's 1, 2, 3, 4, 5, 6, 7. If even turning off might cost energy, right? Might have to flip a switch internally. So that's -7 for actions. Okay, did it suck up any dirt? How much? 1. Okay, so plus 100 for dirt. Did it shut off in the right place?
No.
It did not. So -1,000. Now sum it up. 900 minus 7. Okay, 893. All right. Negative 893. Not very good. Okay, we good? All right. Well, that's the idea. Okay, so now let's talk about how we can actually build these agents. This is one of the simplest of 4 architectural sketches. So this is the environment, and this is conceptual, right? So this is an environment. This is not specific to anything, any particular environment. This is you typing at the keyboard, or it's backpack moving in the office, or it's a UAV on a battlefield. We just don't know. So it's an environment, okay? We have our sensors are watching that environment, producing what? Percepts, right? Here, okay? A percept is a view of what the world is like right now, right? According to its sensors, right? Which may be limited, as in the backbox case. And the way you build a reflex agent is you just have these very simple condition action rules. If you bump, turn right, right? Keep you from hitting the wall forever if you're a backbot, that kind of a thing. And these rules for every percept tell you what you need to do next. Okay? You send that action out the effectors, and the world changes. You get a new percept, and around you go. Okay? Good? Okay. That's the simplest possible one. Now, simplest, maybe least capable, but simple's nice for engineering, right? Building complex systems is a cost. We like to build them as simple as possible. However, for the backbot specifically, if we wanted to have it do this, we wanted to have it actually go vacuum up all the dirt, go back to its original position and orientation, shut itself down. Do you think you could do that with a reflex agent?
I think you could. Yes, would certainly not be efficient.
Okay, all right. A reasonable guess. Anyone else have a different guess?
Well, the other guess is it can't, so I'll guess that one.
Well, I'd want to know the reasoning behind it as well. Good point, though.
You could make the argument that if
Yeah.
like it's either just gonna be going randomly, or we're gonna have to follow its rules. And if you don't tell it what the layout of the house looks like, and you don't know the layout of the house, you're gonna have to give it some rules that you hope will result in it going into every room, checking every space.
Right.
Instead of it getting, it could do a loop that resulted in that it's good and it's back in the spot in the original orientation, in which case it shut itself down.
Solid reason. Okay. But in fact, in this case, there's actually a way to look at it where you see, nah, it's clearly crazy. Okay, why? Because if you look at the VacBot, assume you could do it. Assume you could do it. It turns on, it gets a percept, it does its little thing, goes, vacuums up everything, comes back here, shuts off. Okay, what's the last percept it will get before it shuts off? What is it?
Home.
Home's part of it. It's 3 bits.
Yeah.
I want 3 numbers from you.
001. Yeah.
001. Okay. Let me ask you something. What's the percept it will get when you turn it on?
Same.
The same thing. The reflex agent isn't complex enough to deal with that. You have to pick for 001. Go right, go ahead, go straight on, shut yourself off. It has to be one specific thing. So if it has to be off, then it's gonna come on and it's gonna say, oh, I need to turn off. It's going to be the most frustrating and useless vacuum bot you've ever could possibly conceive of. Okay, but this is the thing. But sometimes you can get good answers with reflex agents, and they are the easiest to build, and they're very fast, and they don't use much computation, and they have all kinds of advantages. So when you can get away with it, it's important to consider it as an option. All right. All right, I have some words here. Hopefully I covered it well enough. Let's go to the next one. This is a model-based, so it's a reflex agent, but a model-based reflex agent. So what's different here is that the raw percepts are not what the conditioned action rules directly act on, okay? Instead, the percepts is this extra loop here where we develop some sense of state. So state means what's going on in the world, right? So this often makes all the difference. Right? So in our state, we could keep track of, okay, is this the very first percept that I have? And if you knew it was the very first percept, you could solve the problem of the VacBot just shutting off right at the beginning, right? You could say, normally you shut off when you get a 001, but not if it's the first percept you have, then you will go forward. Okay? So this often makes all the difference. If you have a reflex agent, likewise, if you imagine a kind of a sentry agent that shoots at bad stuff that it sees, okay? It shoots at what is visible in the percept. If it was a plain old reflex agent, once the bad guy goes out of sight, what does the sentry do? It's gone. It's like it was never there. Bang, bang, bang. Oh, no, everything's good. Everything's good. Everything's fine. But it has no way to remember that, no, right over there out of sight, there is something bad. Okay, but here, if that happens with this design, it's on you, because then you decided not to have your state remember that there is a threat in the area. Not a mistake I think most of us would make, right? So this becomes a much more powerful way, still simple if-then rules, which are cool. We can all code if-then rules. You don't need me to teach you how to do that. You need a basic programming course, right? So that part is cool. All right. All right, now the next thing, next more complicated kind of design, is a goal-based agent, okay? Now the issue with this is that goals are abstract, right? So the other agent took the percepts and it takes an action. Actions are concrete, right? But here we assume that we're now to say stuff like, go to the top of the hill, go to the mess area, right? And the robot will somehow turn that into valid action. So this is a much more complicated type of design. The jump between the first two and the third one is big. 1 and 2 are kind of similar, 3 and 4 are kind of similar. Okay. So what would you need to do in order to decide whether a given, say you're a VacBot, whether a given action gets you closer to the mess or not? Well, you would have to have some kind of additional knowledge, like what does going forward actually do in terms of changing the state of the world? And if you realize, well, I'm here, I'm at these coordinates, if I go forward, I'm over here, now you have some chance to try to think about, okay, did I improve things or not, given my goals? Okay? You also need to know, well, how the world evolves. Okay, actually, that's more what my actions do. Going forward, what does that change? How the world evolves is just what the other things in the world do, right? Like if someone's moving and is going to move right into my path, well, that needs to be factored in for me to decide what's the good path to go to the mess. You know, if something bad is happening over here, someone's moving into an office, I maybe need to go around the long way, you know? All right. Questions about this? Okay, this is much more powerful. Okay, it still has some. It still could do better, right? The problem with it is that a goal is a Boolean thing. You know, you're in the mess or you're not in the mess. That's fine for simple stuff, but it's not good enough to make agents to perform well in a simulation, right? So it's not just like win the battle, like that's a very clear thing, right? I mean, even if you could say wipe out all the bad guys, okay, or you could say get yourself to the top of this hill, okay, you could say those things, but there are many ways to get yourself to the top of the hill. Some maybe use a ton of fuel and a ton of ammunition and take a lot of time. And other ways may not do none of that and get you there quickly with little expenditure. There's no way to discriminate that here. Just that you either did it or you didn't. Your plan was good. If it got you to the solution, it's good. Okay, that's a little too simple for most of our needs. We need often to go have something more complex, which is instead of a thumbs up, thumbs down, you reach the goal or not, a floating point number, a utility. You know, how well, what utility means usefulness, right? So how well did I actually do? Right? If you failed completely and you never got to the top of the hill, clearly you did bad. You're not going to get a good utility number for that. I saved fuel and ammunition, but I didn't actually do what you told me to do. Okay, not very cool. Okay, but this will allow us to say, yeah, two ways of getting to the top of the hill. One is more expensive than the other. The more expensive one has less utility. The other one has more utility. Please give me the better one. Okay. Again, in order to do this, you still need all this extra knowledge. This is never any easier. This is each sketch gets more difficult to build. Okay? You still need to know how the world's going to evolve, what your actions do, yeah. Whereas with the goals, if you find one path to the mess, you can stop, right? Because I got one. It'll reach the goal. If you're in this framework, it's like, yeah, but is that the good way to reach the goal? You're not done. You got to keep thinking, well, maybe there's other ways. Is there something better that I should be thinking about? Yeah, that's the reality. All right. Now, I'm going to very quickly give you several terms, just 5, that I tend to use in terms of what can make environments difficult for agents to perform well. One is that they could be inaccessible. This is a weird term. What it actually means is you can't see everything. Partially observable is a better term, right? Every battlefield is inaccessible in this range, but some are really inaccessible and some are less inaccessible. This always makes things worse. It's always worse if things are random, i.e. non-deterministic. These things are coupled together, right? Often things that we coarsely say, oh yeah, that's random. Like you roll a die for a board game to tell you how many spaces to move. We think, oh, that's random. Oh, we know that's not actually random, right? Physics tells you that's a deterministic process. However, it is inaccessible because you don't see the die in the person's hand and you don't know where it starts. Okay, and you certainly, even if you could compute all the physics, okay, a computer can compute all the physics, and the die would not be random at all if you could see the starting position and the forces that are placed on the die, right? We know that. Okay, so these two are closely connected. A dynamic environment is always harder. Dynamic environments are changing while you're doing your decision making, right? And we all know in warfare, it's very important to be fast, and you want to be good in your decision making, but also fast, in particular, faster than your opponent. So he's responding to you and you're not responding to him, right? That's where we hope to be. Not all environments have this bad characteristic, right? Like again, like if you take chess as an alternative, it's not, you can't mess with the board while I'm making my move. You have to wait for me to think and come to my decision, right? Some environments are more like that. It's always worse if the environment is continuous, meaning that when you go and model it, you realize that you need floating point numbers, not just Booleans and things that are coming from a small finite set. Okay, that always makes things more difficult. And last but not least, non-episodic. Non-episodic environments mean no do-overs, right? You don't get to, if you don't like the way the war is going, you can't go back to the beginning and start again, right? Actual wars are non-episodic, episodic, but war games on a computer are episodic. You're like you did badly, and the whole point is you're just trying to learn, so you can hit restart and go back to the beginning and try again, right? Some environments are like that. All right. Any questions on all that? That's the end. We made it. All right, I don't know if I'm going to make it to the, you guys have to go off to King Hall, I guess. And I don't know if I'm going to make it or not, but I will try. And if not, I hope you guys can spin me up tomorrow.